All right, guys, so today we're going to talk about plasmas. So, plasmas exist as a substance broken into positive and negative particles. All right, so all plasma is particles, just like liquids, solids, and gases, but they're broken up into negative and positive particles. All right, plasma is a very good conductor of electricity, and you guys will see as we talk about the different examples of plasma. It makes sense that plasma is a very good conductor of electricity. So plasma, like gases, has an indefinite shape and an indefinite volume. Remember, what we mean by this is it could take any shape. There's an infinite amount of possibilities of shapes that plasma can take, and there's an infinite amount of volume that it could take up. All right. So, where is plasma? You might be looking around like, oh, Mr. Harris, I don't see any plasma, on Earth, right? The only plasma we have really on Earth is lightning. Lightning strikes are a form of plasma. Other than that, most of the plasma that we have in the world or in the universe is in space. All right. So first bullet here. Through solids, liquids, and gas, or though solids, liquids, and gases are the most common state of matter on Earth, plasma is the most common in the universe. All right. So stars are made of plasma. Our sun is a star. That star is made all of plasma. Lightning contains plasma in it. Then we have things like neon signs, which all neon signs are noble gases that we use heat to light. So currently, scientists are trying to find a way to contain a plasma without energy loss. Right now, we can create a plasma, for example, neon signs. So we can create plasma, but we're still losing energy when we do create plasma. So how could that be beneficial to life on Earth if we could have plasma that didn't take energy to create? So I want you guys to think about that and write that on your paper. And I'll give you guys the answer to that at the end of the PowerPoint. So the particle movement in plasma. So the negatively charged electrons, which are these yellow guys here, are freely streaming through positively charged ions. So in a plasma, the electrons are storming past the blue positively charged ions. All right. This is what makes them such a good conductor of electricity. So next we have energy. All right. Energy is the ability to change or move matter. In order to change a state of matter, energy must be added or transferred. And this just goes back to all the way in the beginning of the PowerPoint where we talked about the different states of matter. And we told you guys that as you increase the energy in something, you're going to change that state of matter. So solids, they're very low energy. Their particles are just moving really, 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 they're just like vibrating a tiny, tiny small amount. Then we get to liquids, which liquids, their particles are moving a lot more freely. They're like kind of sliding over each other, right? Then we have things like gases, which if I were to show you a box right here and show you guys the gases in this box, the particles are very spaced out. And you guys can kind of see that there. And then next we get to plasmas, which you have just positive ions floating around and then negative ions zooming past them. All right, so as you add energy, so this arrow here is going to be as you add energy. So I even put add energy, your state of matter changes. All right. So what types of changes are there? there are two main types of changes that we're going to talk about regarding energy in or going out of an object. And these are just things that you're going to have to remember. And these things are going to follow you guys around for the rest of your science career, I promise you. All right, so our first term that we're going to want to remember is endothermic change or endothermic reaction. This is when energy enters. I kind of like to look at the word endo and say, okay, endo kind of sounds like into, okay? So an endothermic reaction or endothermic change is when energy enters that object, okay? Energy entering that object. So an endothermic change might be something going from a solid to a liquid, right? Because energy is entering the solid, or which is going to change it to a liquid. So like heat entering an ice cube is going to turn it into water. Next, we have an exothermic, which you probably guessed this already. Exo means exit, which is going to be the exact opposite of an endothermic reaction. So in exothermic reactions, we have energy leaving the system. And remember, think about like temperature, right? So let's say I have a glass of water here. Here's my glass of water. And I'm going to try to remove energy from this glass of water. In other words, I'm going to decrease the temperature because that's the same as removing energy. When I decrease this temperature below 32 degrees Fahrenheit, what is it going to change into? An ice cube, right? So I put this in the freezer, let it freeze. I'm taking away energy. I'm performing an exothermic reaction. And I'm now going to go back into that freezer and see a glass of ice. It's just going to be a plain big old block of ice. All right. That's an example of a exothermic reaction. So here's just a helpful chart so you guys can see. As you add energy, as energy enters, endo enters into, you go from solids to liquids to gases to plasmas as you get more energy. So this side I will write as more energy. On the other side, as you have less and less and less energy in a system, as your energy is exiting, or you're performing an exothermic reaction, exo exit. As you have less energy, you're going from a plasma to a gas to a liquid to a solid. So a solid to a liquid we call melting. And a few of these you guys are going to just know right off the bat, right? These sound familiar to you. So when you go from a solid to a liquid, you melt, right? And that's an endothermic reaction. Sorry, some of the word is cut off. It's an endothermic reaction. Next one, we have freezing, all right? So which is a liquid turning into a solid. So if you go from a liquid to a solid, like water to an ice cube, right? That is going to be exothermic. Energy is leaving the system. So boiling and evaporation, all right? So that's when you go from a liquid to a gas. That's like if you have something on the stove, right? You have water in the stove. That water is evaporating. It's turning into a gas, like a gaseous state, right? And that's what we call, and that's another endothermic reaction, and that's what we call boiling or evaporation. And you guys have all seen this before. If you've ever cooked or ever boiled water, I'm sure all you guys have done this before. Next, we have condensation, which is something turning from a gas right to a liquid. You've probably been inside of a car before. I'm gonna try and replicate a car window. You've probably been in a car before, or or even on the bus. You're on the bus in the morning. You're looking out the window, right? And it's the glass is cold maybe, but it's still kind of warm out outside, and you see like the little droplets on the window, but it's not raining. That's what we call like condensation. Or it's a really, really hot sunny day outside, and you take a glass of nice cool lemonade outside, and people might say, or you've probably heard someone say, oh, your drink is sweating. It's not really sweating, it's just the cold glass of that cup. As soon as it reaches outside and it gets hot and the glass starts to warm up, that rapid change is going to create the water vapor in the air to instantly change from a vapor to a liquid. Right? So that's what we call condensation. All right, next, guys, we have two of them you may not have heard of before. The first one we have is sublimation. Is when you change from a solid directly to a gas. So example of this is a perfect example. We have dry ice. So this is an endothermic reaction. It is a change from a solid directly to a gas. So this is like poof, right? A lot of kids get mixed up with sublimation and vaporizing. Not the same thing at all. You're just going from a solid to a gas. Vaporizing is when something completely disappears off like the face of the universe. All right, so changing states, real quick, last slide. It does not change the composition or the mass. All this is saying is theoretically, if I have a glass of water, or I pour 50 milliliters of water into a cup, and I stick that cup in the freezer. When I go to remove that cup from the freezer and I get that ice, I should theoretically have 50 milliliters of ice or 50 milliliters of water still, right? And that's what we call the law of conservation of mass. Mass cannot be created or destroyed. There's no way that I can lose mass by going from a different state of matter. The next thing is the law of conservation of energy. So this is energy cannot be created or destroyed. Energy can be lost from the system, or it can enter the system, but it cannot ever be destroyed or created. The same amount of energy we have today in the world will be the same amount of energy we have tomorrow, and the next day, and the next day, and the next day, and the next day, and the next day. All right, that's all for today. I'll see you guys later.